Hello everyone, my name is Leanna Kalinowski and I am very excited to be presenting on Open Science 101 to all of you today. So for the next 30 or so minutes, I'll be providing an introduction to open science in hopes of you hopefully applying these principles to your research, whether it's through your Climate Match Academy project or beyond that. So I was asked to introduce myself and my background. So I am currently the manager of science engagement research. Another title of mine is the Civic Science Fellow at Neuromatch. And broadly, I am interested in improving the gap that exists between scientists and society. And I do that through things like research, toolkit design, and lectures like this. Prior to joining Neuromatch, I was a scientist with interest in both neuroscience and public health, and the bulk of my previous research focused on substance use disorders. From that, I'm also very passionate about science engagement, whether it's policy, advocacy, communication, and of course, things like open science. Really, any way that I can bridge that gap is really important to me. And then on a personal note, I grew up in Buffalo, New York in the United States, and I currently live in Ontario, Canada. Okay, so before I go into the content of today's lecture, I wanted to make some acknowledgments. So I first want to acknowledge the fact that while I am the one speaking to you today, my former colleague Hlib was instrumental in developing the materials for our Open Science 101 course, which this is a derivative of. So a huge shout out to Hlib for his incredible work on these materials. I would also like to acknowledge the NASA Open Science 101 team and their collaborators for originally developing the open science training materials and making them open source and allowing for us to adapt their materials to our needs and the spirit of open science. So without Hlib and without the NASA Open Science 101 team, he probably would not be seeing this presentation right now. So huge thank you to all of them. Okay, so today's lecture will be divided into 3 sections, and I'm going to start with an introduction into what open science is. So what is open science? According to the United States Office of Science and Technology Policy, open science refers to the principle and practice of making research products and processes available to all, while respecting diverse cultures, maintaining security and privacy, and fostering collaborations, reproducibility, and equity. Now, I suspect that this definition is a lot broader than your current understanding of open science. Open science is so much more than just publishing open access or just posting your data to a repository. There is a lot more that you can make open about your science than what you might have originally thought. So if you come away from this lecture with any key information, I hope that that is one of your key takeaways there. Okay. So why does open science matter now? Now, there are several current challenges in science that make open science more important now than ever before. So I'll walk through each of those and outline how open science may be counteracting some of these current challenges. So the first challenge that I want to introduce here is the current public pushback against science that we are seeing. This has led to an increase in skepticism among the general public. However, when you introduce open science principles marked by these red arrows here, you can involve community feedback into the research process, which then could lead to increased transparency and accuracy. Another challenge is the reproducibility crisis, which refers to the fact that most published research cannot be reproduced by other scientists with the information that is publicly available to them. This has led to really a public loss and confidence in research. And so through open science, this can counteract this by introducing more avenues for peer review and public scrutiny, thereby enhancing the robustness and credibility of your research. And then the last big current challenge in science that I wanted to discuss on this slide is the spread of misinformation, which we know hinders public understanding of research. By introducing open science practices, we have more instances where our results and methodologies are publicly available, showing that we don't have anything to hide here, and this can thereby increase trust and understanding among the general public. So open science can be very helpful in many of these current challenges, as you can see here. Okay, so I now want to take us through a couple examples of open science in action. One example that I really like a lot is open science taking the form of what we commonly call citizen science, or incorporating the public into the research process, often through helping with data collection and analysis. One example I really like about this is the NASA Exoplanet Explorer Citizen Science Project. So in 2017, viewers watching a TV program called Stargazing Live were given access actually to an open access database, and they were invited to help NASA sift through the data and identify exoplanets, which are defined as planets outside of our solar system. Now, within 48 hours, over 10,000 participants classified 2 million exoplanets from this data set, and many of these were fairly significant in size. So we had 44 of them that were about the size of Jupiter and 72 that were the size of Neptune, as well as some others that you can see listed on the slide here. And I really love this story because it's an example of how communities can rapidly uncover new results through open science. I think citizen science is more commonly applied in disciplines like astronomy and ecology, but I have several people in my professional network who are exploring ways to make this more common in fields like climate science, which is really exciting. And speaking of climate science, I want to outline a really nice example of open science in action that comes from this discipline, this time highlighting how closed science can delay detections of errors within the original scientific paper. So in 1990, there was a paper published that claimed that there were no signs of global warming. In fact, there was global cooling, and that we don't understand the climate enough to change climate policy. That was their takeaway from that paper. Now, the data for this study were open, but the software used to analyze them was not. So it was really difficult for someone else to go in and reanalyze that. 8 years later, in 1998, other scientists were finally able to take a look, and they actually found a mistake in the original analysis. And when they fixed that mistake in the analysis, they found that the signs of global cooling in the original paper were in fact no longer there. It took several more years for a new version of this paper to finally be released. So that was released in 2003, and that's 13 years from the original paper in 1990 to really correct the error that was made. And it could have been fixed much, much sooner if the software that they use was publicly available from the beginning. Before I move on from the slide, I do want to acknowledge that it can actually feel scary to put your work out there for others to find your mistakes, but I think we can all agree that being able to detect and correct errors is so much better for science. Another sort of area that I want to go more in depth on is the reproducibility crisis that I talked about a couple of slides ago. So the term reproducibility refers to when you use the same input data, computational steps, methods, code, and conditions of analysis as the original scientist, you should be able to obtain the same results that they did. However, it is becoming increasingly evident that this is not the case for many scientific studies out there. And we have some scientific data to confirm this. So in 2011, the journal Science began to require that authors who publish in their journal share their data and their software upon request. So after this policy change, a group of researchers then wanted to go through the articles published in Science and start testing them for reproducibility. So they went through them, they redid their analyses and looked for what they could find. They examined 204 articles for this, and they found that only 26% of those articles were able to be reproduced with the information that they had. The paper outlining this was published in 2018, and the authors noted that the primary barriers to reproducibility included lack of access to essential data and software, as well as insufficiently detailed descriptions of the methods used in the research. These barriers would not be as present if open science practices were more widely adopted. So hopefully over the next couple of years and decades, as open science becomes more popular, hopefully we can increase this 26% number here. Okay, you might be wondering, well, what's in it for me? So let's talk about some benefits of open science to you. For one, open science principles like good documentation and version control can help both you and others understand and reproduce your work. So a bit of a personal example here, I'm currently working on writing up an old project for publication from graduate school, and I have to admit that I did not apply very many open science principles to this particular project. There are some parts of this project that I'm revisiting a year later, and I can honestly say that there are many parts of this project where I don't know what I did or why I did it. And if I would have just used some good documentation from the beginning, I could have saved myself this huge headache and time investment. Another area of importance of open science to you is really lifelong access. So sharing your research publicly ensures lifelong access, even if you change your job or your institution. So I finished graduate school about a year ago, and my school did not waste any time removing my access to Dropbox and other places where I was storing my projects. I wish I would have adopted these principles more heavily by posting things to data repositories like Zenodo and kept my access to everything, but instead I had to go through the process of emailing back and forth with IT and my old advisor to restore my access, which is a huge headache, a huge investment in time, and something that could have been avoided if, like I said, I just posted everything to Zenodo from the get-go. Another area is that best practices in open science can actually strengthen your funding proposals by showing transparency, increasing citations, and delivering better returns for funding agencies. There have actually been several studies that show that applying open science principles to your research leads to more citations on your work. Storing your data in repositories like Zenodo also allows you to generate a DOI for your data, and this basically allows researchers to cite your data, so you'll get credit and citations for the hard work that you put into generating that data set. And then lastly, if you are looking for collaborators, or if you are kind of growing in your career and looking to kind of build your reputation as a scientist, well-documented research actually attracts better collaborators and boosts public trust in your work. If you are being very clear in your documentation, it is a sign that you might be easier to work with and that there won't be a ton of time spent hunting down data in other research products, so that could make you look better in the long run. Okay, so those are the benefits of open science to you. Let's talk about some of the benefits of open science to science. So for first, perhaps unsurprisingly, open science helps to boost reproducibility, which we've talked about. You know, it feels like the method sections of papers keep on getting shorter and shorter, which makes it so hard to reproduce or build upon what other people are doing, right? I don't know if you've ever read a paper where you try to figure out what they're doing and it's just so hard because the methods are so short. So when you make your work open and when others do that, it makes it so much easier to follow along. Open science also improves accuracy of research. So a perfect example of this is that global cooling case example that I just described a couple slides ago. So when people were able to scrutinize the work, they were able to figure out that an error was made and they could put in the time to fix it. Another benefit to science is that open science helps to drive discovery. So things like publicly accessible data sets allow researchers to focus on things like modeling and analysis, thus generating novel discoveries about what it is that they're studying instead of having to reinvent the wheel and collect their own data from scratch. Me coming from a public health background especially, I use a lot of publicly available data sets in my public health work, and this has saved me hours upon hours of time. You know, if someone else put in the effort to collect that data, then it's really easy to go in and adapt those analyses to my needs. And then lastly, open science helps to improve scholarly communication. It helps to mitigate things like publication bias, and it enhances the trustworthiness of literature by promoting practices like registered reports and pre-registration. It also makes it more likely for people to share their null findings or things that were not significantly significant, which can help save a ton of time by making people aware that one of their questions has already been answered, so they don't need to go down the path of trying to answer that themselves. And then lastly, I want to talk about some benefits of open science to society. So for one, open science benefits society by accelerating scientific progress. So open science practices can really promote the rapid sharing of research findings, which enables quicker responses to very rapid societal challenges like we saw with the COVID-19 pandemic, where we were able to develop the vaccines so quickly. Another way open science benefits society is that it helps to improve scientific efficiency. So quite a significant chunk of research is paid for with government funding, depending on the country that you live in. And so by reducing redundancy and promoting the reuse of research data, open science minimizes waste, leading to more efficient use of resources in scientific research, which is often taxpayer funded in many instances. It certainly is in the countries that I'm familiar with, the United States and Canada. And then lastly, open science allows us to attract diverse participants into the research process. So really think about the exoplanet explorers example that we just talked about. We got over 10,000 people to engage in the scientific process who likely otherwise would have never been able to. So that's really nice, that's really exciting, and it incorporates just new voices into this process. Okay, so let's now go into how to do open science, focusing on some practical things to keep in mind as you work to make your research more open. So let's first talk about some things to keep in mind regarding security, privacy, and inclusivity. So on the topic of national security, if you do work in research that has anything to do with military secrets and national security, it is very important that you check any guidelines imposed by your university and regulatory bodies to make sure that you are not accidentally sharing things that should not be shared. So most universities have a legal office for these sorts of things. Similar thing is human privacy. So if you are working with human subjects, it is very important to make sure that you are not sharing sensitive information about these individuals. Again, these guidelines will vary based on your country and institution, so it's very important to double check with your institution's legal office before making information related to human subjects publicly available. If you are working with Indigenous communities, there are specific guidelines that you need to follow called the CARE principles, and this really ensures that individuals in Indigenous communities are having their rights and governance respected. So if you navigate to our course website, you'll be able to find links to the CARE principles if you are indeed working with Indigenous populations. Another thing to keep in mind is environmental considerations. So researchers should assess the potential impact of data sharing on vulnerable ecosystems, ensuring that studies do not unintentionally harm endangered species or their habitats. So we had a student in a previous cohort who was conducting research on wild polar bears, and she mentioned having to follow very specific guidelines to keep the location of the bears private. So as with anything else, this is something that you'll want to check in with your advisor and your university legal offices about to make sure that you're not accidentally sharing things that should not be shared. Like the concerns about Indigenous communities, ethical research practices require that affected communities are included in the research design and that findings are made accessible and understanding to them. So this is just a general guideline. If you are researching a specific community, you should be keeping this community in mind and really co-developing your research projects with these communities to be following the current ethical guidelines related to this. And then lastly, if your work is in any way applicable to environmental justice, it is important that open science prioritizes the fair treatment and meaningful involvement of all communities in environmental policies. Okay, so that's security, privacy, and inclusivity. Let's now talk about intellectual property. So what this is the recognition of rights associated with the content created by human intellect, or the things that you create. There are several different types of intellectual property, and how they are recognized varies based on your country, your type, and the time it has been since the stuff was developed. But in general, it's very important to understand who has the rights to the content that you created. So the intellectual property doesn't always automatically apply to you. Work that you create might belong to your employer. It might be in the public domain, especially if you're a public servant. It might depend on the license of underlying or work that you built upon. It might belong to the publisher that you published your research paper in, or it might still remain your own intellectual property. So the next few slides will go into some things to keep in mind related to intellectual property. But in general, it's very important to sit down and figure out who owns the intellectual property for your research products, because that will guide what you then end up doing with that information. So there are several types of IP protections, so we'll go through a couple of them. The first one and most relevant one to researchers is copyright. And this basically protects original works of authorship. So this can be artistic or literary works, and it also applies to software. In general, and if applicable, copyright is automatically applied at the moment of creation. So you do not need to register for a copyright. If you own the intellectual property, then you don't need to register that. If you own the copyright to your work, this entitles you to select a license for your work. So we'll discuss that on the next slide. The next type of IP protection is a trademark, and this can be applied to any content, including words, phrases, symbols, designs, or a combination of these things that identifies your product. Trademarks in general are not relevant for scientific purposes. Patents. This is an exclusive right granted for an invention, which is a product or a process that provides, in general, a new way of doing something or offers a new technical solution to a problem. So patents are another way to make your work open while protecting your intellectual property. Many organizations have groups that will support the development and commercialization of inventions. Many universities also have offices related to this. And if you happen to be a graduate student and create something while as a student that could be a potential invention, it is very important to check with any legal offices at your university that handle things related to patents, because you might not fully own the intellectual property depending on how that invention was developed. And then in some cases, intellectual property is not protected at all. This is the public domain. So this is when a creative work has no intellectual property rights associated with it. So some examples of this happening, sometimes intellectual property protections expire after a certain period of time. If you're using like an old logo, for instance, and the time expired on that, then you won't need to follow the restrictions imposed by the original protection if it is now public domain. Another example is things created by civil servants in the United States, so they cannot claim copyright on the things that they develop as a civil servant. But in some instances as well, the creator of the work could also donate their work to the public domain, so that there are no longer intellectual property rights that are applicable. So you might be asking yourself, why should I as a scientist care about intellectual property? I want you to consider what happens to the ownership of your research if you were to move institutions. You'll want to ask yourself, can you take your paper drafts, presentations, and copies of publications with you? Can you take your data? Can you take your software? These are things that can be complicated, so it's important to think about these things from the get-go and ensure that intellectual property is straightened out as you are working through research projects. And another thing, even if you don't move institutions, there are other questions that you'll want to keep in mind related to intellectual property. So if you submit your manuscript to a publisher that requires that they own the copyright of the work, will you be able to later access that work when you no longer work for that company, or if you no longer have a subscription to that work? Another question to keep in mind, are you able to meet the mandates of your funding agency to openly share your work? Can you reuse the figures that you made in one paper to the next? Or does the previous journal now own those things? These are very important questions to keep in mind. This can seem like an unnecessary detail early on, but if you anticipate changes to your situation and help ensure and permanent ownership of your work, this can help make your life so much easier in the long run. Okay, so let's talk about licensing. So licensing is a way to help others reuse your work legally. It is a way to specify under what conditions, if any, others can use, build upon, or distribute your work. It is also a method to ensure that your work is appropriately credited. It is generally illegal and may be a form of academic misconduct to reuse content without a license, even if the content can be found on the internet. This law protects content creators just as it protects your work from being used by others without clear permission. Thankfully, it's very easy to allow others to reuse your work. By applying a license to your work, you make it clear what others can do with the things that you're sharing, and also establish the conditions under which that you're providing them, such as citing you as a condition. Now, if you don't license your work, others can't and should not reuse it, even if your intention was for them to be able to. So licenses can be applied to data, code, reports, publications, and almost any other creative output. So if you are creating any of those things, it is very important to consider applying a license to your work. And then logistically, how do you actually apply a license? The good news is that it's very simple. There is no formal application process. All you have to do is choose a Creative Commons license that suits your needs and then communicate that choice in a way that would be clear to the people who come across your work. So as part of this communication, you'll want to include a link to the license that you chose, and this can be either plain text or you can embed the icon of the license type that you choose into the web page that you're using. For example, if you're using a Creative Commons license, they have code that you can embed into that to make it very simple. Okay. And then I just wanted to include this slide in here as a reference for the different types of Creative Commons licenses, but I won't go into these in detail. Okay, and then switching gears for the next 2 slides, I wanted to outline some milestones within the research process and how open science can be applied to each of them. So in general, a research project can be divided into 3 phases: the planning phase, the implementation phase, and the release phase. So planning is self-explanatory. This is when you're getting ready to begin a new project and you start outlining how that's going to happen. Implementation refers to actually running the study, including things like data collection and data wrangling. And then release refers to what you do with your findings after a study is complete, such as publications and presentations. Now, in general, products related to all 3 of these phases of the scientific process are needed to enable others to reproduce the findings. While publishing open access, for example, is a good start, it is not enough if you are not including other milestones of this project. And here's just an updated example on the bottom here. This image now has some examples of some of the products that you can make open. The specialized products that you specifically create in your project may differ. Something you create might not even be listed on this figure. But the focus on discovery for the public remains the same. Any products that you create can be modified to support the principles and concepts of open science. So as you complete scientific studies as a researcher, I encourage you to consider making several of these products openly accessible if it is appropriate for your circumstances. Okay, and for this final phase of my talk, I would like to acknowledge that there are many valid fears out there regarding open science and also some common misconceptions. So for the last handful of slides, I want to quickly go through some of these common issues and explain why you might not need to worry about them as much as you might suspect. So the first fear that I want to talk about is mistakes. What if my work is wrong or inelegant? That's a very common fear. And some things that I want to just lay out here. For one, sharing research publicly might expose mistakes, but this benefits science and society by allowing quick improvements to it. Peer review in general is really great, and it helps you identify and correct errors, enhancing the quality of the work. And I think open science helps shift the perception of mistakes from failures to steps in discovery, which I think is a really important mindset to have related to this. It's really just good to think about, like fixing your work and the impact that can have on science and society. And then just in general, community feedback is crucial for improving research. A very common thing that I've seen is a fear of scooping, or the thought that what if someone reuses my work and gets all of the credit for it? And I want to validate that this is a fear. It can happen, but depositing your work early and making it citable establishes your claim to it. This provides evidence of when you began your work, and it helps others to cite you. And really, scooping can lead to short-term gain, but long-term loss in reputation if it becomes clear that they were not the originators of the work. And in general, collaboration is often more rewarding and leads to greater career success. Another common fear is misrepresentation of my work. And this, unfortunately, is something that can happen regardless of openness of publication format. And really, openness is probably better anyways, because it provides additional context which can help clarify your work. Proper documentation of your research plan and software management helps others fully understand your work. as well as sharing your code, can help reduce the risk of misinterpretation. Another fear is that my work will be used, but it won't be cited. Again, very valid fear, but science ethics require that you be cited if your work is used. So if someone is not citing you, then they are, not engaging in ethical science. Open science values all steps of the scientific workflow, including code, data, and non-published articles. And this can help make it easy for others to cite you if you are doing things like applying DOIs to your research products. Always cite others' materials to avoid contributing to citation issues. And it's always just a good practice to include a citation statement or an example citation on your products to make it easier for others to cite you as well. Another fear is that the data that you have collected is too sensitive to share. And yes, be very, very careful that you are not accidentally sharing information that should not be shared. But in general, if you are following appropriate anonymization or using controlled access, this can help address this concern. This isn't necessarily a fear, but more so a thought. Many people are concerned that if they engage in open science, that they'll have to maintain and update their work. And this isn't necessarily the case. Sharing your work can enable others to reproduce, replicate, and build upon it. You do not have to maintain your work indefinitely or even at all. But even if you don't plan to maintain your code, it's still recommended to share and archive it publicly. Many things like GitHub repositories can help you list out some contributing guidelines to clarify how long you plan to maintain your materials, and can also give people insights into whether their collaboration on that project is welcome. And if others see your work and think it is useful to them, they may offer to step in and help support it. So something to consider there as well. Another fear is that your work won't be useful to anyone else. And really the thought here is you never know how materials might be used. Individuals who contributed to all different types of software projects ended up helping NASA land a rover on Mars. So you never know what it'll be useful to others. And in these last couple of slides, I just want to acknowledge the fact that there are misaligned incentives between how science currently operates and the open science movement. So as you might be aware, current scientific incentives often prioritize publication quantity over quality, and funding and awards typically reward novelty rather than collaboration or infrastructure development, and existing metrics do not often capture the full impact of open science activities, which can hinder the adoption of them. And this affects the adoption of open science, right? Researchers might hesitate to invest time into open science practices due to their lack of recognition. Misaligned incentives can often dissuade collaboration and the sharing of resources, and really a culture shift is needed to align the incentives with the values of open science. I know this is easier said than done, especially if you are early career, but if you happen to be in a situation where you can be a bit of a squeaky wheel and try to encourage your supervisor or others around you to give open science a chance, even if it's just a small piece of the project, I encourage you to do so. The necessary culture shift in academia won't happen until open science becomes more widely accepted. So if this is something that you end up developing a passion for, I highly encourage you to act on that. And then before I let you go, I just wanted to leave you here with this. Open science is a lot of effort, but in my opinion, and the opinion of others, it is worth it. The benefits and ethical imperative of open science outweigh the barriers, and I hope that that is clear from earlier slides in the slide deck. And I think recognizing these barriers is the first step towards overcoming them and advancing the practice of open science. We and I hope that your time as a Climate Match student will serve as a great starting point for being a practitioner of open science, and we and I look forward to supporting you along the way. We actually have a free and publicly available open science course book from our extended Open Science 101 course. The link is on the slide here and will be listed in your tutorial on here. And this contains much more in-depth information about this topic. So we welcome you to take advantage of these resources throughout this course and beyond. And then lastly, here is just the full citation for the NASA Open Science curriculum that this is heavily adapted from. With that, I thank you so much for your time, and I wish you the best of luck in your open science endeavors.